Hi everyone, can you guys hear me?
Yes.
Yep. Awesome. Welcome to the talk AutoML, the assembly line of machine learning. And just like Dan said, my name is Mayur Pawal. I work in the Salesforce Einstein team, and I manage our automated machine learning product initiative. And today, I'm going to talk about our homegrown machine learning library called Optimus Prime, which helps automate the machine learning pipeline. All right, so let's get started. So a little small thing, you guys all know that Salesforce is a publicly traded company, so we have a very active legal team, so this is a forward-looking statement. I was about to explain every single word here, but I'll save you the trouble. Long story short, don't buy Salesforce stocks just based upon this session, all right? So let's get started. You have to do this. Anyways, so I want to talk a lot about what Optimus Prime is and how we are automating machine learning, but I think it's great to set the context and explain why we invested in Optimus Prime in the first place. So you guys were mostly in the keynote, and I think there was a point made about in the real world, building a machine learning is not just about the modeling algorithm. There's a lot of center stage. Machine learning algorithms takes a lot of center stage, but there's a lot of work which goes on into the pipeline, which means ETL, feature engineering. And once you have done your feature engineering, you would actually get into the stage of training your model. And once you train your model, generally all of you who have worked in data scientists and machine learning, you would see that the model generally doesn't perform very well. So that's the evaluation stage, and you have to iterate and train the model many, many times through different parameters. And oftentimes, you have to go back to all the way to your feature engineering process. And then once you do that, you have to go ahead and figure out how do you deploy and operationalize your model. And once you do that, you have to think about scoring, and you have to think about versioning of your models. So a little show of hands, how many of you guys have been involved in actually deploying a model into production? Awesome. And how many of you are actually involved in modeling hundreds of models in production today? That's cool. Awesome. So why I asked that? At Salesforce, we have to do it many, many, many times over. And let me explain why. There are two factors involved. Salesforce is an enterprise company, so we build business solutions for many different verticals. For instance, financial companies, sales, marketing, e-commerce, IoT. An example is US Bank is one of our retail customers. So they're a financial company, and they have like 16.9 million retail clients. And what they want to find out is which of those retail clients would resonate well with their wealth management value proposition, so that their financial advisors can actually prioritize those retail clients and sell them the wealth management solution. Another use case is of their existing wealth management customers, which of those are about to churn or attrite, because they want to retain them going forward and incentivize them accordingly. So US Bank is just one customer. Since we are a business-to-business company, we have hundreds of such customers. And each of those customers' data set looks completely different. It has a different shape and different form. So the model that we built for one customer does not work for another. The second wrinkle here is, I talked about two use cases, but across all of these different verticals, we have many other use cases, and then we have a long tail of use cases. There's some really funny ones that I've heard that, how long does it take for your visa to get approved? We have certain nonprofits which we work with. Would a college student drop out of the college? Then there are some in the logistics department, they say, like, would this truck break down in the next 30 days, and can we predict that ahead of time so that we can solve that problem? So it's a combination of the number of customers. We also call it tenant, so it's multi-tenant machine learning, and the number of use cases across these verticals, which makes it an order of magnitude harder problem for us. It's like a scale of different sorts. The second important thing, all of you are probably aware of this, that machine learning software is different from traditional software. And there are many different ways to actually state that fact, and there are a lot of literature around it. So this is just one perspective, which is any software is actually, at the end of the day, a troubleshooting or debugging problem. We all know that when we build a software, it doesn't work straight out of the box. So you have to go back and tweak it. So in a traditional software, if you see the x and the y axis, there are two dimensions. What algorithm you're implementing, is the algorithm correct to begin with? And second, have you implemented it correctly? Once we get into the machine learning software domain, it turns out there are two additional dimensions which gets added. So the z-axis is model issues. Is your model overfitting? And the fourth dimension is data-related issues. Do you have enough data? Do you have leakage going on in your data? Do you have data which is very messy and not clean? And we all know that, those of you who have done it, that most of the data does look like that. So suddenly, from a two-dimensional problem, it becomes a four-dimensional debugging problem, and hence a bit more complicated. Next, we know there's a lot of different machine learning frameworks. I think the gentleman in the keynote also talked about this. And some call it framework, some would call it library, some would call it platform. And each of them serves or solves a niche use case, a specific application. So if you're starting out, or even with someone with reasonable experience and tribal knowledge, it's sometimes very hard to figure out where do you really start? What do you really use? And all of these factors combined, it turns out there are not enough data scientists in the whole world to do all the kind of modeling that we want to do here at Salesforce. And we want to really do it to actually make it truly accessible to our business customers, who makes it accessible to their end users, to, at the end of the day, the consumers. So how do we really democratize machine learning if we don't have enough data scientists? And that's the motivation that helped us, actually that necessitated the birth of Optimus Prime at Salesforce. So I'm going to talk a lot about that. But the key message, the key value proposition here is, can you build a model which achieves 90% or more accuracy than a handcrafted and a hand-tuned model? But here's the kicker, not with one-fold, two-fold, but 100x reduction in time and effort. So that's what we are focusing on. And an analogy that I like to give is about automobiles. And when cars first came into the market, they were super expensive. And it took a lot of time to build and manufacture each and every one of them. And hence, it was inaccessible to the majority of the population. But then Henry Ford came into the picture. He put cars on the assembly line. And quickly, they got way cheaper. They got, the time needed to manufacture one shortened dramatically. It got way more accessible. So we're trying to do the same thing for machine learning as Henry Ford did for cars. So I'm going to do a little fun aside. There's a quote someone said that in software, there are two very hard things. One is cache and validation, and another is naming of a software. So we were struggling with a lot to find out what would be the right name for this software. So this is a library built on top of Spark and Spark ML and uses Scala as a function programming language. And it's really a collection of transformers, which you can stack one after another to build your assembly line. And so aptly, we named it Optimus Prime after the character from the movie Transformers. But soon we realized that there are some trademark issues duly brought by our amazing marketing and legal team that we cannot use this name. But we were using the abbreviation OP everywhere in the code, and no one really wanted to change it. So we were trying to find a name which fits that OP as an abbreviation, yet it captures the soul of Transformers. So what we did is we removed 4 letters in the word Optimus and replaced it with something called Octopus Prime. And well, we don't know if the name would stick, so if you guys have better suggestions, come to me after the talk. I would love to hear from you guys. But it's a bit ironic, right? It's a library of transformers, and it turns out that Optimus Prime transformed himself to something called Octopus Prime, which we say is like a multi-legged data transformer. All right. So Octopus Prime is our automated machine learning library. It had helped accelerate data scientist productivity at Salesforce by almost a mile. You don't necessarily need to have a PhD or an advanced machine learning degree to leverage machine learning. And you can build predictive applications in hours, not months or releases, which it was taking us before. And many of our customers actually put their data within Salesforce. So we have schema and metadata around that data, so we try to leverage that. That's what I meant by it natively supports Salesforce objects. Because if you know some of those schema and those relationships, you can leverage that in your machine learning, feature engineering, and a model selection process. And lastly, as we are not writing new algorithms, so we are not reinventing the wheel here. So we wrap the Spark ML algorithm. So if there is a newer and better algorithm which is contributed by the community, we would automatically wrap it so you can leverage the ongoing improvements. So I want to pause here and mention one thing, because this comes up from time to time. Like the model that we are trying to build, it does not replace, if you're a data scientist who have tribal knowledge, who have experience in applied machine learning, if you come up with a handcrafted and hand-tuned model, this is no match for that. However, the point that I'm trying to make is how many of us really need a Rolls-Royce to go from point A to B when a Toyota or a Honda can really do the job? So in the next section of the talk, having said the motivation and what this is all about, we're going to go under the hood, and I would really try to explain what kind of automation we are doing. So there are 3 aspects to it. So there is automated feature engineering, there is automated feature selection, and then there is automated model selection. So we'll talk about each of them a bit. So here's an example of automated feature engineering. So these are some of the features we have. So in this library, you also have a rich hierarchy, type hierarchy, so you can define a feature as email, which is very common. Feature as a phone. Age is a text feature, age is a numeric feature, subject is a text feature, and zip code is a special kind of feature. And so depending on this type, this is again just a snapshot, we would figure out if this email is spammy or not, and that's a new kind of a feature we derived or transformed from the original feature. Another very common thing that we do, we would extract the domain of the email and we would do one-hot encoding. So you can imagine if someone has a Gmail address versus a Hotmail address versus a Yahoo address, it might mean different thing. Also, in our context, sometimes we also have to figure out if it's a business address or it's a consumer or a personal address, because that might mean something different. Phone, we would extract the country code, the area code, which actually has a lot of signal about what the location is, and then we would also figure out if the phone is valid or not. So imagine someone going to a company website and signing up for some white paper and putting in their phone number. The likelihood of that person converting to a real user would be high if they really put their valid phone number versus they putting something spammy. Age is a numeric feature. We would automatically bucketize numeric features into buckets. Like in most of the libraries, you have to manually select the buckets. You have to say from this to this. But how do you really come to know like what those buckets would be? So we use decision tree behind the scenes to actually figure out what those buckets would be based upon the information gained. Subject is a text feature. We would do top TF-IDF terms. We also do hashing, tokenization, and some of the other stuff. So I was saying zip code is a special kind of feature because it gives us an opportunity to also augment. So we can use other external data sets. So based upon zip code, we can bring in, for instance, average income and actually make your features richer than it was to begin with. And all of this, we would then vectorize and create those pretty numeric 0-1 matrix, which most of your machine algorithms are actually desire or require, because you cannot feed any of these features in the format in which it is. And as I said, this is the tip of the iceberg. So this is kind of more expanded, comprehensive scope that we have done based upon the type of feature it is. For example, numeric, we would do automatically null indicators, because if a lot of features are null, it might have very interesting signal. Imputation strategies, smart binning, which I just talked about, scaling and log normalization. For categorical feature, we would do all of those, and then we would do one-hot encoding. We would also do dynamic top-k pivot. What is that like? I was just giving an example of email addresses, but imagine state, right? There are like 50 states in the US. But if your data is mostly has the top 10 states, maybe you can do top 10 of those and the rest are others, so that your feature engineering space doesn't get exploded. On the text side, tokenization, hash encoding, TF-IDF, word-to-vec. We also embed sentiment analysis and language detection, because many of these text features are really dependent on what language you're using. Time-based features, time difference is important. Many time feature also captures seasonality, because if there is seasonality in your business, we would do circular statistics to capture it. Time extraction, that is day of the week, week of the month, month of the year, and so on, and closeness to major events. So if there's a Christmas, Thanksgiving, or some event happening, it might be a very important signal. For spatial features, we would do geoencoding, the example that I talked about, augmenting with external data, and some of the other stuff we are working on in our roadmap. So, and another thing that I want to mention, like each of these, like even if you think about imputation, there are tons of research papers how you can do imputation. Like you can just fill it up with a mean, or you can fill it up with the 0 or null, or you can actually do some crazy regressions just to figure out how you would impute. So like for someone, what we have seen earlier, what was happening is like we have different teams, different data scientist teams and machine learning teams. Each of them were coming up with their own different implementation of imputation. And at times we saw, though the implementation was very different, the goal was the same. So there was a lot of repetition and a lot of redundance. And so we put all of this research into place, and because this is some of the repetitive work, so we were trying to automate these things so you can just call this and immediately get value out of it. Okay, so that was automatic feature engineering. The next is automatic feature selection. So what do I mean by that? So each of these features that we fed in, we would actually compute descriptive statistics around it, such as min, mean, max, number of nulls, variance, standard deviations. Why? Because many of these features might not have acceptable ranges. That's what the real-world data looks like. For instance, if you have an age feature and you have negative values, there's something wrong with that feature to begin with. So we need to detect those things automatically. Next, we would do associations of these features with the label. So these are examples of correlation. R is a correlation measure. If R is high, it's good, because this is a feature with a good signal. If R is 0, this means this feature does not really have any predictive signal. It's garbage. So based upon that, we would drop features which are not very helpful, and so limit the feature space, which can actually help in how fast you can iterate on the modeling part. This is the second part of automatic feature selection, and this we have seen a lot in enterprise data space, which we call data leakage or label leakage. This happens when information from the label creeps into your current feature. And this is a real-world use case. I was talking about the lead score. Lead score is the predicting what is the likelihood of a lead converting to a sale. And these are the top predictive factors. And what we saw was there was this feature called lead value, which was there in the data set. And it was getting filled up with an estimate the moment the lead is about to get converted to a sale. So you can imagine that if you use a machine learning algorithm with this feature to train, it would perform great in your research environment. It will probably get very 0.99 accuracy. But in the real world, that feature won't really be available, and your model would perform very poorly. And this is just an example, because our businesses use different kind of ETL processes, different workflow processes, different methods of entry data. And there's a huge problem in the data entry. And so because of this unknown business processes, this is a huge bottleneck, because if you cannot solve this, we can't really get to the next stage of creating realistic models. And finally, the automated model selection. I think most of in the industry, when they talk about automated machine learning, they really just focus on automated model selection and not some of the steps and the stages that I talked about before. And automated model selection has, again, two parts. It's automated hyperparameter tuning. So this is the space of hyperparameters, and we are trying to find the best hyperparameter. And I stole this GIF animation from the guys at Sagat, which I really liked. Like, how can you take a complex algorithm and actually visualize it? So there are three different approaches. If you see the space is where we are trying to find the hyperparameters. The yellow dots are actually the hyperparameters. In a grid search, it's kind of dumb. It just goes line by line, trying to figure out, oh, is this the best hyperparameter? But it can work pretty well, depending how small your data set is and how good your use case is. Sometimes dumb methods really work well. And then we have random search, which gets slightly smarter. And then we have Bayesian search, which is a much more intelligent approach. Might work great with bigger data sets, because a grid search might just never complete with a big, complicated data sets. And there are other advanced methods, intelligent approaches that you can use for your hyperparameter tuning. Like you can use a genetic algorithm or a particle-based approach. We haven't done all this thing, but this is still kind of future work, kind of in a roadmap. So depending upon the class of machine learning problem that you're trying to solve, whether it's a regression problem, binary classification problem, or multi-class classification problem, we would use, together with those hyperparameters, we would compete different models. For instance, in regression, we would use gradient-boosted trees, decision trees, random forests, GLRs, and see which model performs the best for this data set. This is important, because the same model might not perform the best in all kinds of data sets that I talked about in the beginning. And this is one of my favorite slides, actually, in this presentation. Like, if you're wondering, like, OK, you're doing automated feature engineering, model selection, feature selection, but what is the point? Like, what are we really trying to get out of it? And the point is, like, you can use a combination of all of these tactics, and each of this, I'm saying it's a method. And you can see that the difference between method 1 and method 13, even if I eyeball, it's like 500% increase in your evaluation metric, whichever you choose. In this case, it's just an example. We are using AUROC. And traditionally, a data scientist would actually do all of this like manually. They would try different feature engineering. They would try different models. And they would see the results and go back. And it takes a lot of time. It's very time-consuming. And we're trying to see how we can get to that much faster so that we can actually build these predictive applications much faster. So basically, a diverse set of features and models can lead to very different results. OK, so this is my Disneyland slide, and which is, like, once we use all of these models, all of these methods, we have been able to reduce the time that has taken us to build predictive application from months to hours. And we are doing, so this is actually powering our underlying platform, which actually helps our customers build predictive applications. Today, we are doing more than 1 billion predictions per day on this platform. And this is another very interesting slide. It's a time period of a year. How many models were deployed to production completely hands-free? There used to be a y-axis. It was removed because of PR comments, so cannot show it. Would have loved to show it. OK, so let's recap. So I talked about that machine learning is slightly complex. It needs a lot of PhDs. There are an overwhelming number of technologies. It's time-consuming. It's really hard to scale. Like building one model to production is hard enough. Like when you have to build thousands of such models to production, it really doesn't scale. Optimus Prime was born out of necessity at Salesforce. It's our automated machine learning library. And the key value proposition is here, again, is can we achieve 90% or more accuracy? Again, I'm using accuracy as like a superset of all evaluation metrics. It can be something else. With 100x reduction in time and in effort. And today, OP is our Salesforce internal platform, and it's powering hundreds of enterprise customers, truly democratize machine learning to our business customers and to their end users. And with that, next slide. Thank you. Questions, comments? Yes.
Who's going first?
Did you, John?
You got a lot of dimensions of exploding quantities of data, both features, number of models, amount of like rows of data.
Yes.
Presumably using Spark to parallelize all that out, but
yes.
on which dimensions are you parallelizing?
So each of those models would be parallelized, so what we are running, and we also parallelize sometimes the feature engineering process. So.
So you mentioned something about data leakage and not getting. Do you have any ways of automatically figuring out if your data is correct in some sense or not?
Yes.
Like encodings of wrong or different definitions of variables across time, stuff like that.
Can you repeat the last part?
Different definitions. If a variable changes definition across time, do you
yes.
have any other ways of detecting
so, this is a really good question, and thank you for that. And so initially, I showed some examples that we were doing some kind of a correlations with the label. But correlations works great if your data is filled up many of the times and it's not very sparse. And correlations also works for numeric features who are monotonically increasing or their association is related to that of the label. It doesn't work very well for categorical features, for instance. If you have a categorical feature with only 3 values, it would work. But if you have 10 or 20 values, then it doesn't work because the other feature values would dilute the total correlation that you're having with that label. So that's why we started investing in Kramer's V. We started seeing lots of other problems, like text feature in Salesforce is notorious. Everyone dumps everything into text. So not all of these are really text features. So we have to do cardinality analysis on some of those text features to figure out, are they really text or they are numeric or categorical? So we can apply different feature engineering process. One of the bigger problems, which you are kind of hinting at as the data that we are often training on is shifting, it's drifting. And the actual data that we're scoring on looks very different. So we are doing a distribution analysis between our training and the scoring data. Like we're looking at the fill rates of each of these features. Like how do the distribution look like to figure out that if it's the fundamental assumption of machine learning is the data that you're training on is similar to the data that you're scoring. So through those distribution analysis, we try to figure out that if there is a problem. And so flag it. Maybe we have to retrain it. Maybe we have to drop certain things. We have seen other very interesting issues like there's a certain feature which was very, very important, which was used, suddenly stops getting used. And there's a new feature which was never used before starts getting used. And you talk to the customer, they say, no, we are still using this feature. But then we look at the data, no, you're not really using that feature. So one of the joke here at Salesforce is as we're trying to build those machine learning applications, what we have seen is it has made our customers look more closely into the data which they have never really looked into before. So it's not a solved problem. It's a really hard problem, especially when it comes to the difference between the leakers and the true predictors. Like it's about the thresholds. And we're still working on it. There's a lot of research going on into it.
Thank you. Hi, I'm a pretty heavily user of Salesforce. So,
awesome, thank you.
Just a quick question on the output of that. So when you define a lead to be more likely to become a sale, What is the time range there, and how do you use the output of your prediction and trend it over time if it doesn't become a sale, for example? Yeah, that's it, I guess.
Yeah. So if I understood the question correctly, like it's very easy to say that a lead has converted, a positive label, but how do you really figure out it's a negative label? Like when do you really do that? And I think it really depends on some of those use cases. Like we actually look at the distribution, like the leads, and how long does it take, how long does it stay. And then based upon that, you can actually figure out that what should be the timeline where in some cases it's like 30 days. Like if they haven't converted within 30 days, then they're probably more likely to be negative example. In some data sets, it's not 30 days, it's 50 days. So again, it's the same thing. Like we cannot use just one threshold and do it. I think there is another talk, I think later today, like the folks from Open Door is coming. And I've heard this similar talk before. I think they're talking about like, how do you really predict your house is going to really be sold, and like how long is it the market? And they would probably talk about like, you know, when it's sold, you really know, but if it's not sold, you don't know what's really happening. And they talk about different strategies to do that. For them, it's slightly easier because you're just looking at houses and sales. For us, like leads is just an example. For a different use case, it might take a year to actually, the attrition use case, for instance, I was talking about, or churn or college drop-off, sometimes you have to wait for a year worth of data to really figure out that if this is really a negative signal or not. So it's hard. Yeah.
Hi. So training different types of models can obviously take a long time, but then adding in parameters can add exponential amount of time. So have you guys looked at, I guess, which parameters for certain models are coming up recurringly and like change the way you guys choose the parameters? Like, have you been smart about like which parameters you've chosen?
We haven't, but there is a thought process on a similar line. So let's say if you use certain hyperparameters and you're training an algorithm, and you can learn from the previous one and actually store it somewhere, so you can retrieve it and don't start from the scratch again. Yeah. So that's where you can parallelize. Actually, computationally, it's much easier from that perspective.
Okay. Cool.
But Spark really helps to parallelize, and if you really parallelize things in the proper way, I think that helps a lot. One more thing that I wanted to mention, which is related to this. So this is all the training part, which is kind of happening right now in the batch mode. So it kind of takes time, but once you actually figure out the model, the scoring part is much more faster. So in the training time, it does take some time, but it's like, well, the alternate is much worse, right? You know, it would take months. So, yeah.
Do you ever find there are tensions between the sort of desires of the different machine learning algorithms and the transformers and their output? So if you're, for example, one-hot encoding your categoricals, and decision trees would really like to have every option available to split on, but a regression would prefer that you drop one and let the intercept capture that. It seems like there might be a tension there in terms of what those models want.
Yeah, so actually this happens. So I talked about the auto-bucketizing thing that I was talking about. So like in numerics, we'd figure out buckets. We're actually using, it's kind of like an ensemble model. So we're using a decision tree to actually figure out those buckets, which is great when you're using something like a logistic regression and stuff. So one of our data scientists said, it doesn't really help when you're using a decision tree, because that's what a decision tree or a random forest do to begin with. So like we would use that with a decision tree or not use that with, we'll use that with a logistic regression. And with a decision tree, we won't auto-bucketize, and we would try those different approaches, because sometimes random forest or decision tree does not always work best. Like I know that random forests are generally a winner in most of the cases, but not always true. But yeah.